So, we continue our applications of concepts of variable area ducts, shock waves, expansion waves in problems. So, here we take simple problems, not too many variety of concepts are used. So, a nozzle in a wind tunnel gives a test section Mach number of 2. Air enters the nozzle from a large reservoir at 0.69 bar and 310 Kelvin. Cross sectional area of the throat is 1000 centimeter square. Determine following quantities for wind tunnel under one dimensional isentropic flow consideration, that is quasi 1D flow. Pressure, temperature, velocity at throat, pressure, temperature, velocity and area of cross section at the test section, and mass flow rate. So, this is direct application of varying area duct principles. So, what is known is throat area is given. So, this is a nozzle problem. So, you have a nozzle and exit Mach number is given. So, Mach number is 2.0 and that is also known that 0.69 bar and 310 Kelvin are P0 and T0 and area at throat is known. So, AT is 1000 centimeter square. So, let us see how to go about this problem. Pressure, temperature and velocity at throat. For this at throat at operating conditions for a supersonic nozzle, throat Mach number is 1. So, a Mach number is 1. So, P star by P naught and T star by T naught are the values to consider, and this is 0.528 and this is 0.834. Okay. So, these values you can get from isentropic tables or calculators. So, then pressure at throat is just multiplication by P naught, which is 0.69. So, this is 0.365 bar and T throat is 258 Kelvin. So, we get 258 Kelvin here. Okay. And from this we can also calculate what is the velocity at the throat. Velocity at throat is equal to A star, that is speed of sound, Mach number is 1, square root of gamma RT 1.4 288 258. Okay, multiplication, this is 323 meters per second. Okay. This is the value. Now, we go to what should be the pressure, temperature, velocity at the exit. So, it is an isentropic flow, completely an isentropic flow. Mach number is 2 at the exit. So, ME is 2.0. So, PE by P naught. So, PE by P naught is 0.128, TE by T naught is 0.555, and since we need to find area of cross section, we need to know A by A star. This is for Mach 2, it is 1.687. So, pressure at the exit is 0.0885 bar, temperature at the exit is 172 Kelvin and the area is 1.687 multiplied by 1000, 1687 centimeter square. So, what is the mass flow rate? Mass flow rate, it can be calculated at throat, rho t, Vt, At, all things are calculated here. Density at throat can be calculated by Pt by Rtt, it is 0.49 kilogram per meter cube, and Vt is known 323 and At is known 1000 centimeter square. So, that is 0.1 meter square. So, this turns out to be 15.827 kilogram per second. So, here in this problem directly we are using a variable area duct principles, mass flow rate principles, and isentropic flow through variable area duct. So, this is a straight numerical example. Second one is an under expanded 2-dimensional supersonic nozzle. So, here we have an under expanded jet. So, an under expanded flow in under expanded nozzle flow, the nozzle pressure at the exit. So, P exit at the nozzle will be greater than the ambient pressure Pa if it is ambient pressure, then P exit will be greater than ambient pressure. So, there is still pressure left for expansion. So, as a result the nozzle the flow undergoes an expansion through a centered expansion fan. If we take the so, if we take that quasi 1D flow through nozzle, at the exit you will have a uniform flow, and thereafter you can take a centered expansion fan and the nozzle the flow will expand. So, flow will turn across the centered expansion fan. So, if you zoom into this, so it will be like this. So, here we use principles not only of quasi 1D nozzle flows, we also use expansion wave principles here. So, what is given? Exhaust into a region where pressure is 0.75. So, here pressure is 0.75 atmospheres, that means at the edge here also it should be 0.75 atmosphere. But at the nozzle exit plane at PE at exit at the section exit, pressure is 1.6 atmospheres, 1.6 atmospheres. So, clearly it is a case of an expansion under expansion, and Mach number is 2. So, within the nozzle flow is quasi 1D, it is uniform, but outside the nozzle it will now expand. So, calculate Mach number and flow direction after the initial. So, this expansion happens. So, what is the Mach number here after the expansion and the flow direction? So, it has now expanded, it flows outward. So, what is that direction? We know pressure ratio, is known. So, if I take this as region 2 and region 1, P2 by P1 is given, P2 by P1 is 0.75 by 1.6 atmospheres. This is given to us. Okay. So, how do we go about this problem? Flow through the nozzle is flow through the nozzle as well as the expansion, centered expansion is isentropic. So, it uses isentropic relations. If exit pressure is 1.6 atmosphere, then the corresponding P naught for M2 operation, we can find this out, because P1 by P naught is 0.1278 for Mach number equal to 2. So, P naught is 12.52 atmospheres, and this P naught remains the same across the centered expansion also. So, P naught 2 is equal to P naught 1. So, P1 P2 by P naught 2 is 0.75 by 12.52 is 0.06. So, here you get Mach number at 2 is 2.48. So, now we have found out the Mach number at 0.2. So, now we need to know what is change in the angle theta. Theta is from Prandtl Meyer expansion relations nu of M2 minus nu of M1, where nu is the Prandtl Meyer angle, and Prandtl Meyer angle you can read out from tables or you can use a calculator. 38.651 minus 26.37 degrees, which is 12.281 degrees. So, you have used two concepts here. One is a quasi 1D flow in the nozzle, and then an under expanded jet, and in the initial expansion you used Prandtl Meyer expansion relations. So, connected concepts being used here. Okay. So, in the next problem, a normal shock occurs in the divergent section of the convergent divergent nozzle. Throat area is 1/3 of the exit area, and static pressure at the exit is 0.4 times that of total pressure at inlet. Flow throughout is isentropic except through the shock. Determine Mach numbers before and after the shock, area of cross section of nozzle at the section where the normal shock occurs, static pressure before the shock. So, what is given? Let us see. This is a nozzle, and area ratio of this nozzle is given, exit area and throat area, AT. AE by AT is 1 by 1, AE by AT is 3. So, that is AE by AT is 3, and somewhere here one shock occurs, and P exit to P01. P exit by P01 is 0.4. So, this is given. How do we go about this problem? So, this uses concepts of shock in divergent passage. So, what we know is, so if I name these as 1 station number 1, 2, 3, 4. So, this is what I would say. So, what we are given here is A4 by A1 is 3. It is given A4 by A1 is 3, and what is A4 by A star? In this particular case, it will be A4 by A1 is equal to A4 by A3 star. So, A4 by A3 star, because there is a normal shock here, okay, multiplied by A3 star. So, A4 star or A3 star by A2 star. So, A3 star by A2 star. So, A2 star will be equal to A1, because this is a supersonic flow. Here Mach number is 1, and here all through this region A2 star will be equal to A1 star, or A1 equal to AT. But A3 star will not be equal to A2, because there is a stagnation pressure loss across this shock. Okay. So, this is the principle we use. So, now what is the guiding principle here? This A3 star by A2 star, A3 star by A2 star are related. A3 star P03 A3 star is P02 A2 star. So, A3 star by A2 star is P02 by P03. So, this is A4 by A3 star multiplied by P02 by P03. So, if we can find out what is P02 by P03, then we can find what is the Mach number, but this is A4 by A1. So, this is equal to 3. Okay. Now, what is given about P02 by P01? So, now P03 by P02, P03 by P02 is A4 by A3 star multiplied by 1 by 3. Okay. This is known. Now, we know P4 by P01 is given. So, P4 by P01 is given. can be written as P4 by P04, okay, multiplied by P01 is constant all through until the point 2. Okay, so P4 by P04 is so this is known, P01 is known. So P03 by P02, can we write it in terms of P4 by P04? This is what needs to be understood. P03 is the same as P04. So P03 is equal to P04. P03 by P02, I can write it as P04 divided by P4, okay, and multiplied by P4 by P01. Yes, so we can give this value because P02 is equal to P01 and this is equal to P04. Yes, so we can because P4 by P01 is given, this is equal to 0.4. Okay, so now we get an equation P04 by P4 multiplied by 0.4 is equal to A4 by A3 star multiplied by 1 by 3. Now this can be expressed only in terms of Mach number M4. This can be also expressed only in terms of the Mach number. Okay, so this can be expressed. So we can write this as 1 plus gamma minus 1 by 2 M4 square the whole power gamma by gamma minus 1 multiplied by 0.4 is 1 by M4 1 plus gamma minus 1 by 2 M4 square gamma plus 1 by 2 or gamma plus 1 by 2 gamma minus 1 multiplied by 1 by 3. So this you can solve for M4 and M4 can turns out to be 0.4718. Okay, so now if we know this value, then P04 by P4 is known, is 1.1646. Therefore P03 by P02 can be found out, the 0.4658. Okay, now once P03 by P02 is known, then Mach number is known. So the Mach number of the shock is 2.58. So M2 is 2.58 and M3 is 0.5056. Now we know 2.58, so this is the case. Mach number equal to 1 here. At section 2 Mach number is 2.58 and there is a shock there, and then you have section 3 and 4. Okay, so if you know 2.58, you know the area ratio. So area ratio is A2 by A2 star is 2.842. So this is the area ratio at which the shock occurs. So this example is a nice example where connected concepts are given about shock waves in divergent ducts and pressure ratio across the nozzle which creates that shock, and you had to find the area ratio and Mach number at which the shock is located. And so with this these simple problems involved direct concepts of area ratios. Now let us see when this kind of concepts are applied into multiple examples or cases where you need multiple concepts or you want to apply it in some situations, then how will we apply these principles in the next class.